Ganesh sir, you there?
Yeah, yes.
So you are ready to start?
Yeah, yeah.
Okay. Okay. Dear participants, it's an honor to introduce to you my colleague from EC department NIT Silchar, who will be presenting today in this session. So let me give a small introduction about him. Ganesh Prasad sir, Dr. Ganesh Prasad sir is an assistant professor of EC department at NIT Silchar. He completed his MTech in communication systems from IIT BHU, and eventually he did his PhD from NIT Silchar. He has a rich 8 years of experience in teaching and research, and also a brief uh, experience in industry with ST Microelectronics. Prior to joining NIT Silchar, he has also served as a assistant professor at NIT Raipur. His research interests include 5G plus networks, G2D communication, IoT, cooperative wireless communications, underwater networks, free space optical communications, green communications, deep machine learning, and graph theory. He has published articles in reputed journals like IEEE Transactions, IEEE Communication Letters, and have also published research articles in many flagship conferences, along with book chapters in domains of communication engineering. At present, he has reviewed. He's one of the reviewers in many of Indian edition of Digital Communication Systems by Simon Atkins, which is one of the best-selling book in communication engineering that we all are accustomed with this book. He has also recently chaired a session in flagship IEEE BIMRC conference held in London. Keeping all this in account, he also has a rich experience of collaboration with reputed research institutions like Linköping University, Sweden, UNSW, Sydney, then University Central Supélec University of France, and Huawei France Research Center. Enrich us with his domain expertise. Ganesh sir, please continue.
Yeah. Thank you, Dr. Chandish sir, for my introduction. So I will do the Google Meet in presentation mode now. So now it is visible to everyone. Chandish.
Yes, sir. Your screen is visible. The slides are visible. Yes.
Okay. So good afternoon, everyone. Today I am going to present a discussion on green wireless networks. Especially, I will discuss about the trade-offs and design issue in green wireless networks. So this is the conventional cellular system where many base stations have been deployed, and the shape of the cells are hexagonal. In one cell, one base station is there. That is, in common language, we know base station as a tower, mobile tower. And inside the base stations, the users are there. You can see the mobile handsets are there in all the cells. And the mobile handsets communicate through its own base stations, and accordingly, the communication in conventional cellular system is established. So you might study in wireless communication in your coursework. So I will start the discussion on the trade of power consumption in cellular networks. So you can see in base stations in cellular system, the most of the power consumption is taken place by base stations. So you can see here 16 around 60% power consumption is taken place inside the base station itself. And you can see the around 20% mobile switching centers, it consumes around 20% power. So you can see what is mobile switching center. The mobile switching center is connecting all the base stations. And core transmission consumes around 15%. So core transmissions just like it connects more than one mobile switching centers. And data centers is just like routing or other managements is taken place in data center. So it consumes around 5 to 6% power consumptions. And other retails consumes around 2 to 3%. So you can see in power consumption inside the base stations. So this is the statistics inside the base stations. Around 10 to 25% of the total power consumption inside the base station is due to air conditioning, and that is around 17.5% of the total power consumption over the base station. And here you can see in signal processing it consumes around 5 to 15%. Power supply it consumes around 5 to 10%, and power amplifier, which is the main component of the base station to which the signal is transmitted to the users. It covers all the users. So it consumes around 50 to 80%. So now, you can see this is the trend of deployment of base stations over the developing countries. So you can see the orange one is showing the off-grid base stations, and the blue one is showing the on-grid base stations. So what do you mean by off-grid base station and on-grid base stations? So off-grid means there is no proper power supply is there due to the power grids. So power grid generators are not there. So these base stations rely only diesel generators, local diesel generators. So that is not good for the environment, because you know the diesel generators works on diesels, and they emit lots of CO2 footprints. So, and the blue one works on conventional power grids. So you can see in developing countries, you can see in 2007 the total deployment of off-grid base station is around 10 lakhs, more than 10 lakhs, and in 2012 it is around 22 to 23 lakhs. So you can see the trend, how much the increment is there of the deployment of base station, because the users are increasing day by day. So demand of mobile stations is increasing day by day. So that's why accordingly the deployment of base station is also increasing day by day. So that's why it's very important to design the green wireless networks. Okay. So in conventional cellular system, you can see different types of cells are there. So it depends on the size of the cells. So you can see here macro cell is there, micro cell is there, pico cell is there, femto cell is there. So from the figure, it is evident that a macro cell is having the highest range of coverage. So I will show the range of different cells. So you can see here, this is the macro cell. So macro cell range is in kilometers. So it is covering around whole city or even the surrounding suburban areas. So It's a range in kilometers. Micro cell cover the city in the range of hundreds of meters, and pico cell covers the range within the building. So in metro cities, the buildings are there of many floors. So pico cell we use for the coverage of all the buildings, and femtocell is used for the coverage of the range inside a house. So you can see its range is tens of meters, very small range. So depend also corresponding antenna size will be of less efficiency. So now the corresponding power consumption you can also see there. In macro cell, the transmit power is more than 10 watt, and in micro cell the transmit power is 5 to 10 watt. So you can see these two cells are only deployed only for the outdoor. But pico and femto both works for outdoor as well as indoor. So outdoor, just like around the building region or building campus. So you can see for the outdoor, it is 1 to 5 watt transmit power is there, and for the indoor, 100 to 250 milliwatt is there. And in case of femto cells, the outer transmit power is 0.2 to 1 watt, and for the indoor, you can see 10 to 100 milliwatt transmit power is there. So it depends on the different application or the coverage. If you have to increase the coverage efficiency in the cellular cell, then you have to decrease the cellular size of the cell. So you can see femtocell gives the maximum efficiency of coverage, because in cellular cell, the cell is used for the frequency use. If you have studied the wireless communication in your graduation, so you have seen that we use these cells for the frequency use. So if you are a large number of cells are there in a given region, then maximum reuse of frequency is there. So you can see the small cells, femto cells, large number of femto cells can be deployed over a given field. So maximum possible utilization of frequency is there. So depending on the frequency, but the drawback is that we have to deploy maximum number of base stations. So the cost of the hardware will increase. So this is the typical power consumption model over the base stations. So typically, in practice, the power consumption model over the base station is not linear, but for convenience in analysis, the approximate linear power consumption model has been proposed in the base station. So you can see this is the PD is the total power dissipation, and PT is the transmit power by the base stations, that is the mobile tower, and P naught is the total power consumption where the minimum transmit power is taking place from the base station, and delta P is, you can see the constant factor depends on the base station type. So 4 types of base stations are there, you can see. In macro, so P max is 40 watt, P naught is 12 watt, and delta P 14.5 is there. Similarly, in micro, 6.3, 106 watt, and 6.35 is the delta P. Similarly, pico and femto is having these system parameters. So now we will discuss about the motivation for the green wireless network design. So why actually it is motivating us? Because for any research, there should be a motivation for the designing. So it is important that what is the advantage of designing such system. So first, you can see in communication over worldwide, nearly 1100 to 1800 terawatts hour electricity is consumed. So that is nearly, if you combined the Germany and Japan as a whole, so what is the total power consumption over the Germany and Japan as a whole? So that is approximately equal to the total power consumption over the communication worldwide. So you can see it's consumption rate. And the second thing is that already we have discussed that many of the base stations in developing countries are rely on diesel generators. So that's why they are emitting CO2 gases. So you can see CO2 emission is not good for our environment. And the next motivation is that because today's traffic, data traffic is increasing day by day. So you can see, for example, if you have to understand the power consumption dependence on the data traffic, if you take the example, if you play a video on weekly basis for 1 hour, then if you calculate the power consumption over whole year on weekly basis, then it is approximately equal to the annual power consumption by the 2 refrigerators. So you can see how much power consumption is taking place due to the smartphone. If you play a video for 1 hour in a week. And the next motivation is that the day by day, the data traffic is increasing. You can see in 2010, from 2010, nearly 89 times the data has been increased in 10 years. So now you can see the two ways are there for the designing of green wireless networks. So what are those two methods? So first is communication technology perspective. Here you have studied about the 7 different layers in OSI models. Okay, so in communication, 7 different layers are there. So in each layer, in this method, in each layer, we apply the policies or schemes for the reduction of power consumption by working on different parameters over the layers. In second method, you can see it is based on system design perspective. Here we do the power management over the infrastructure, and also we design the low processors which consumes low power processor which consume less power. So now one of the challenges coming in designing of green communication is that due to the heterogeneous network. Now today there is no conventional cellular system is there. In conventional cellular system, you can see that is the homogeneous network where one type of cell is there. Either it is cell or femto cell or pico cell or any other cell. So, but today the cells are combination of all these cells. Okay, so today the cells are combination of all the cells. I think it is connected. Let's check. Okay. So you can see here the base stations are there, but in the base station different types of cells are there. You can see the macro cell is there, micro cell is there, pico cell is there, femto cell is there. Also, even the sensor wireless sensor network is also there. So sensor network, you can see this rely on the multi-hop communication. So different combination of network is there. So that's why this is heterogeneous network. But the challenge in a heterogeneous network is that we have to study all the parameters of the different types of networks for the optimization, for the minimization of total power consumption over the network. So this is one of the challenge over the heterogeneous network. So now we will study about the basic trade-offs in the wireless communication. So for studying the basic trade-offs over the wireless communication, because the study of trade-off is very important for the any optimization. Here the minimization of total power consumption is nothing but we have to optimize the system. So for that we have to study the trade-off of the power consumption with other system parameters. So here fundamentally we will study about the 4 different trade-offs. So first trade-off is spectral efficiency, energy efficiency trade-off. So what is there in this trade-off? Here the bandwidth is given, and we try to balance the achievable rate, that is the data rate, and energy consumption over the system. The second trade-off is deployment efficiency and energy efficiency trade-off. Here we try to balance the deployment cost, throughput, and energy consumption over the network. Third trade-off is bandwidth power trade-off. Here we have fixed data rate, the target data rate is there, and we try to balance the bandwidth of the system as well as the power consumption over this system. And delay trade-off, delay power trade-off is there. So what is this trade-off? Here we try to balance the end-to-end traffic delay, because from one end to other end, if you are transmitting the traffic or data, then it will take some time to reach there. So that is the delay, service delay. So here we try to balance the delay and the power consumption over the network. So we will try to study the few basics about the different trade-offs for point-to-point communication. So what is point-to-point communication? Here in point-to-point communication, you can see one transmitter is there and the other side the receiver is there. So here transmitter is directly communicating with the receiver. So this is the point-to-point communication. So here you can see, okay, for the spectral efficiency and energy efficiency trade-off. Here, what is spectral efficiency? This is nothing but the throughput, that is the data rate achieved. Throughput here means the data rate achieved per unit bandwidth consumption. So this is the spectral efficiency. And what is energy efficiency? Throughput, that is data rate achieved per unit energy consumption over the network. So for characterizing this trade-off, we will apply the Shannon capacity formula. Well-known Shannon capacity formula is there for the AWGN channel. What is AWGN channel? That is the additive wide Gaussian large channel. So what is there in this Shannon capacity? You can see here in Shannon capacity, you can see the R is the throughput, W is the bandwidth of the channel, and this is R is actually equal to W log 2 1 plus P by W N naught. Here N naught is the power spectral density of the additive wide Gaussian large, and P is the transmit power. So now how we will characterize the trade-off? So using this formula, we will try to characterize the trade-off. So first we will find the expression for the energy efficiency, spectral efficiency. So spectral efficiency, you know, that is throughput per unit bandwidth. So here we have to take the ratio of R by W. So using equation 2, so here the equation 2 is there. To take the ratio of R by W, that will be equal to log base to 1 plus P divided by W N naught. Now we will define the energy efficiency. So energy efficiency, you know, throughput achieved per unit power consumption, that is R by P. So that is nothing but, again, using equation 2, you divide R by P. So this equation 4 you will achieve, that is equal to W by P log 2 1 plus P W N naught. So now using these two relationships, we can relate energy efficiency and spectral efficiency. So if you using this equation 3 and 4, you can obtain this one, equation 5, by algebraic simplification. So you can see there is no monotonic relationship is there. You can see spectral efficiency is also in numerator, and in denominator it is at the exponential at the power of 2. So there is no monotonic relationship is there between energy efficiency and spectral efficiency. Now we will study about the second trade-off, that is the deployment efficiency, energy efficiency trade-off. So here still we have to define the deployment efficiency. What is the deployment efficiency? Already we know that deployment efficiency is throughput achieved per unit deployment cost. Here deployment cost, what do you mean deployment cost? Because we are deploying the base station or deploying the transmitter and receiver. So for deploying the transmitter and receiver, we have to spend some money. So that is the deployment cost. So here you can see we are defining the deployment cost eta D, that is equal to R by C. C is the cost, the money you are spending for the deployment of the transmitter and receiver. So that is defined by, again using equation 2, you divide R by C, that is W by C base to 1 plus P by W M naught. So again using equation 6, because this is a trade-off between deployment efficiency and energy efficiency. Already we got the expression for energy efficiency using equation 4. So using equation 4 and equation 6, after algebraic simplification, again we can find the relationship between energy efficiency and deployment efficiency. So again you can see there is no monotonic relationship is there. The deployment efficiency is also there in numerator, and in denominator it is in the power of 2. So now we will study about the third trade-off, that is the bandwidth power trade-off. So bandwidth power trade-off already we have defined. So here you can see because bandwidth and power is both are the important resources for a communication, because both are in limitation, both are in limited amount. So bandwidth is also licensed bandwidth is there, and power is also, we have limited power. So what is this trade-off? So you can see again you can find this trade-off using the Shannon capacity using equation 2. You can see equation 2 is there. Equation 2, what you will do, you express power in terms of W. You rearrange this equation, you will get this equation. Simply you rearrange this one. So here you can see on left hand side we have P, and on right hand side we have W. So P is as a function of W, and other parameters rate is fixed. So this is giving the trade-off between power and bandwidth at a given rate, that is data rate. So now you can see this is monotonic. Here we find the monotonic relationship between power and bandwidth. If you have high bandwidth, means W is large, then R by W is less and 2 by R by W is less. So power is decreasing with increment of bandwidth. But you can see if you take no limitation on bandwidth, means W tends to infinity, then if you apply limit W tends to infinity, then this P will be reduced to this one, N naught R ln 2. So you can see this is the minimum power that can be transmitted to achieve the rate. Below that you cannot achieve the rate R. So this is the minimum power. If the bandwidth, the condition is that bandwidth is infinite. So now you can see the last trade-off we will study about, that is delay power trade-off. So here you can see in the previous trade-off all the parameters were on physical layer. You can see this energy efficiency, you can see all the rate, data rate, and P, power, all these parameters on physical layer of OSI model. Even this case also, okay, power and bandwidth is also on the physical layer. But in this case, you can see we are taking the delay. Delay is on the upper layer, not on network layer. So delay, we are finding the trade-off between the delay and power is on the physical layer. So this is the trade-off between the interlayer. So here you can see we can define this trade-off by first defining what is the delay. So delay is nothing but the reciprocal of rate. Why it is reciprocal of rate? You can see rate is nothing but the bits per second. and reciprocal of rate is nothing but the time taken per bit. So this is the delay. Delay is nothing but the time taken per bit. So now you can see again using equation 2, that is Simon capacity formulation is there. So here you simply, or using equation this one, equation 8, you put R equal to 1 by tau. So you will get this equation. Equation 10, P equal to W N naught to 1 by W tau minus 1. So here again you can see, if you increase delay, if delay is in the network is very large, then this quantity 1 by W tau is going to decrease, and to the power 1 by W tau is going to decrease, then automatically your power transmission is going to decrease. And if you require very less delay, so it is very desired that over the communication delay should be very less. So for that you can see you need a high power. So these are the trade-offs with power. So again, this is also the monotonic relationship. You can see directly we can tell that for high power we need for less delay we need high power, for high delay we need less power for a given bandwidth. So now these trade-offs, 4 trade-offs we can study here to plot. Here 2 scenario has been taken. One is ideal case and other is practical scenario. So in ideal case, you can see the first trade-off we have studied about the spectral efficiency and energy efficiency trade-off. So here you can see with spectral efficiency, if you are going to increase the spectral efficiency, at the same time energy efficiency is going to decrease. Or if you are increasing the energy efficiency over the communication, then your spectral efficiency is going to decrease. So this is the trade-off between spectral efficiency and energy efficiency. Here the deployment, D stands for deployment. So deployment cost and energy efficiency trade-off, you can see if you increase the energy efficiency over the communication network, then your deployment cost is going to decrease. And if deployment is going to increase, then your energy efficiency is going to decrease. So this is trade-off between these two. Again, here the trade-off is between power and bandwidth. So again, you can see if you are going to increase the bandwidth, your power consumption is going to decrease. At the same time, you can analyze this way that if you are increasing the power, then your bandwidth is going to decrease. Similarly, this is a trade-off. It is showing that the power and delay. If your power consumption is going to decrease, then delay over the network is decreasing. And if delay is going to decrease, then your power is going to decrease. But in practical scenario, because these are the trade-offs have been drawn in case of point-to-point communication, where in the presence of additive wide Gaussian noise. But in practical network, there is no point-to-point communication. Even there is multi-hop communication, and also other management is the other system parameters are there. So complex system is there. In that scenario, this curves is no longer existent. We can see in practical concerns the curves of the trade-off is going to be changed. So you can see the spectral efficiency and energy efficiency trade-off. You can see the bell-shaped curve is there. So at certain point you will get the maximum energy efficiency as well as the spectral efficiency is going to be optimized. Similarly, in the energy efficiency deployment and energy efficiency trade-off, you can see some point is there where the energy efficiency is going to be maximum for a given deployment curve. So depending on the network parameters, we have to get the optimal solution for the maximization of energy efficiency and reduction of deployment. Similarly, you can see here the power and bandwidth trade-off is going to be changed in the practical system. So this is the curve. Similarly, in the case of delay and power trade-off, again the curve has been changed. So according to our network assumption, the parameters taken in the network, we have to optimize the network. So it is not like that the ideal case behavior of the trade-off will be there in the practical system. So now still we have studied about the general scenario for the study of trade-off. So now we will take a special case. We will take an instance scenario where we will try to minimize the power consumption over the network. So here we have taken that the n sensor nodes have been deployed over a field. So you can see S1, S2, S3, S4, and Sn. These are the sensor wireless sensor nodes. So you might know about the wireless sensor nodes. So these nodes having the job that they will detect the different phenomena over the environment, and accordingly after sensing those phenomena, they will generate the data and they will send their data to their destination. So that is the job of the sensor nodes in brief. So here n sensor nodes have been deployed over the field, and what we will do, we will try to establish a strong connectivity between these nodes, because in sensor nodes we have to make the connection, then only the data can be forwarded from one node to other node. So here we will try to make the connection between all the nodes to a new node. That is, you can see this is a type of a star topology where the star node is acting as a central hub. To that, all the nodes are communicating. So for this scenario, now our job is we will try to formulate the problem for this case for the minimization of total power consumption, under the constraint that we have to establish the strong connectivity. What is the term strong connectivity? We will understand later on. So here you can see this is our problem formulation. Here the n sensor nodes has been deployed over the field, and now we are trying to optimize the location. So here the location of the S node is going to optimize so that the power consumption, because if the distance between the two nodes is going to increase, then the power consumption in the communication is going to increase. Because in conventional system, if the transmitter and receiver is at long distance, then large amount of transmit power is required for establishing the communication. So that's why we have to optimize the location so that the distance among all the nodes could be minimized. And if the distance among the nodes is going to be minimized, then your power consumption is going to be reduced. So that is our goal, that we have to optimize the location of new node acting as a central hub such that a total power consumption is minimum while maintaining the strong connectivity among the nodes. So what is a strong connectivity? We can briefly say about that. You can see here a little bit we have this has been discussed about the strong connectivity. If a strong connectivity means if two nodes Si and Sj is there, if two nodes Si and Sj is there, then if Si is transmitting power like that, then such that it is covering the Sj node. Similarly, the Sj is transmitting the power like that, it is covering the Si node, then bidirectional communication can be taken place between these two nodes. It means that Si can also transmit the data to the Sj node, and Sj node also can transmit the data to the Si node. So bidirectional communication is going to be established between these two nodes. So that is the strong connectivity. So we have to assign the power on Si and Sj nodes such that the strong connectivity between these two nodes can be established. So for the study of the system, we assume that the n deployed nodes, so you can see these n deployed nodes having the location x1, y1, x2, y2, and xn, yn. So where x is the x coordinate and y is the y coordinate of the location. So now you can see here the transmit power of the sensor nodes is decided by this one. You can see Pi equal to Pj is equal to T dij power alpha, where dij is the distance between the two nodes Si and Sj, and alpha is the path loss exponent over the wireless channel, which range is between 2 to 4, and T is the scaling factor, depends on the amplifier over the transmitter. So this is a constant. We for the analysis we have taken T equal to 1 and alpha equal to 2. So this is the transmit power from the sensor nodes. So now you can see the central hub. What is the transmit power of the central hub? So you can see here, okay, this is P1 power is transmitting to cover this one. This is transmitting P2 power to cover the node S node. This is transmitting P3 power to cover the node S node. Okay. Similarly, S4 and Sn will transmit. So what is P1? P1 is nothing but T already I have taken 1 and alpha already I have taken 2 for our analysis. So this it will depends on the P1 power will depends on the distance square. Distance square. You can see this is Pi. You can see I equal to 1. So P1 is nothing but D here I equal to 1, and because we are taking this central hub J equal to 0. So D10 and alpha is 2. D10 square. So distance square you can see. So this P1 will be distance square between S0 and S1, and this P2 power will be distance square between S2 and S0. Similarly this one. So this will able to cover this S0. But what about, so here the communication will take place in one direction from S1 to S0, S2 to S0, S3 to S0, S4 to S0, Sn to S0. What about the opposite direction? So here you can see S0, how much power should be allocated so that it can also communicate to all the nodes. So here, that's why you can see here, I will take the maximum of the distance square, to cover all the nodes by the new node. So what is the maximum distance we will try to find and take the square, and that much of power we will assign here to cover all the nodes. So then only the bidirectional link will be established and a strong connectivity between the nodes can be established. That's why equation 11 is giving the power assignment over the new node. So now we have to minimize the total power consumption over the network. So what is total power consumption? Here you can see it's all N nodes is having the transmit power, and S node is also having the transmit power. So total power is summation of Pi, I equal to 1 to N. So this is giving the sum of the power over all the nodes, and P node is the power over the S node, new node, that is new node. So this is total power consumption over the network. And now our problem formulation P node. So here in literature we have written the problem P node. So now mathematically we can formulate like that. Here we have to minimize this total power PTOT. Here PTOT is given by equation 12, and the constant is that our strong connectivity. Here the strong connectivity, how you can establish the strong connectivity? Our constant is a strong connectivity. How you can establish the strong connectivity? It is showing that the P node is always greater than or equal to Pi, where I is from 1 to N. So P node, if P node is going to always greater than or equal to Pi, then P node can communicate to all of them, and Pi is already connecting to the S node. So that's why this is the constant for the strong connectivity. So this is the mathematical formulation, and now you can see here for finding the optimal solution, we have to find that whether the problem is convex or not. So you might listen about convex problems. So what is convex problem? In brief, we can understand here. So if the problem is convex, then whatever the solution is you are obtaining, that will be the global solution. If you are trying to find the optimal solution for this convex problem, then that solution is a global solution. Global solution means, in simple language, you can understand this way. If you y equal to x square curve, y equal to x square curve. So I have not drawn here. Okay, let me. I can draw here. I can draw here. So okay, let me. So you can see here. Suppose what is global minimum? So you can see here. So suppose this is your axis, this is x-axis, and this is your y-axis, and this is your, suppose this is your parabolic curve. Okay, this is your parabolic curve. So this is not a smooth. So this is parabolic curve. So suppose I'm taking this simple one. I'm taking this simple one so that I can write the mathematical formulation for that. Or even I can also write the mathematical formulation for this also. That will be equal to y equal to x minus some constant. Suppose I'm taking the constant x naught. Okay, I'm taking the constant x naught. X naught is a constant, and plus, because y shift is there, so y naught is also another constant. And this is whole square will be there because this is parabolic. Okay, so here it is. You can see so that this is a convex function. How you will show that? The criteria for convexity for for a function of one variable, you take the double derivative of this one. So double derivative of this one will be del square y by del s square, and that will be equal to, you can see this will be equal to 2x or 2 only. You can say that is greater than 0. So you can see it is showing that it is greater than 0. It means that there will be a global minima is there. So in basic, in a school education, you have studied about the global minima and global maxima. So in this case, it is global minima. Here some one minimum is there. Similarly, if you take this negative of this one, so this curve will be changed like that. So actually, okay, I should take some eraser. Okay. Okay, so I will take the new page. Okay, so here you can see this plot will be like that. Okay, so this plot will be like that. Okay, this plot will be like that. It's shifting. So just like a reflection from x-axis. So you can see here now it is global maxima is there because the expression is y equal to minus x naught whole square plus now here it will be, because negative as a whole I have to take, so here it will be negative, not positive. So negative I have to take. Okay, so I am taking it negative. So it will be negative and y naught. And if you take the double derivative of this one, so del square y by del x square, then that will be equal to -2. It is less than 0. So you can see again it is having the global maxima. It is having the global maxima. So that's why this function is convex. So similarly, we have to show that the problem is convex. Then only our solution will be global. Means only one optimal solution is there. Unique optimal solution is there. Otherwise, if the curve is like that, you can see if the curve is like that, then here two local maxima is there. So no global maxima is there, two global local maxima is there. So one maxima is here and the other maxima is here. Similarly, for the local minima, you can see here one minima is there and the other minima is here. So this is here you cannot find the global minima. So similar concept is there for the convex problem also. So you can see here in the convex problem, so I will check whether connectivity is there or not. So Chandish sir, connectivity is there or not? Everything is okay? Chandish sir?
Yes, sir.
Yeah. Everything is okay?
Yes, sir. Yes.
Okay.
So your slide is not visible. Your slide is not visible. I think because yeah.
Now
Yeah.
So now we will study about this convex problem. What is the convex problem here? So still we have formulated this problem. Now we will try to prove that whether it is convex problem or not. So for that, the objective function. What is the objective function of any problem? The function at which we have to do the operation, whether I have to minimize or maximize. That is the objective function of the problem. And constant is that under the constant, these are the subject to, inside the subject to the constant of the problem. That I have to minimize or maximize PTOT under the constant of this. So we don't have to violate these conditions. Okay, some conditions should be there inside the optimization. So for the convexity of the problem, we have to prove both the quantity. That's the objective function as well as the constants are convex. If any of them are not going to be convex, then our problem is non-convex, and whatever the optimal solution we have achieved, we cannot claim that that is the global optimal solution. Yes. Changes anything? Okay. Okay. So now we can see here. Now we can see here. So first we will try to determine the convexity of the objective function. So what is the objective function? So for finding, because our objective function, you can see this is the objective function. Here Pi, because we have to minimize, you can see here PTOT actually has to be minimized with respect to three variables, x0, y0 and p0. But you can see here the PTOT is a function of three variables, x0, y0 and p0. x0, what is x0, y0? This is the x0 is the x coordinate of new node s0. Y0 is the new y coordinate of location of the node s0, and p0 is the transmit power by the node s0, denoted by the star. Okay. So here the three variables are there, and we have to minimize PTOT using these three variables under the constant given by Ci, where Ci is n constants are there, where I is going from 1 to n. So now you can see the for examination of the convexity of the objective function, we have to find the Hessian matrix. In the previous case, in this case, if you are going here, in this case, you can see y is only a function of x, only one variable there. So for finding the convexity of this one, you simply take the double derivative of this one. But if the function is a function of more than one variable, then you cannot simply take the double derivative of the function. In that case, you have to find the Hessian matrix. So you can see here the Hessian matrix is there, because our PTOT is a function of three variables, that is x0, y0 and p0. So for that, you can see we have defined the Hessian matrix. For more study about the Hessian matrix, you can take some standard book, or Even you can type on Google, you can they can briefly explain you that what is Hessian matrix. So this is in this form, and in that case, for finding whether the our function, objective function, is convex or not in this case, so we have to find whether this Hessian matrix is semi-positive definite or not. For finding the semi-positive definite, you have to check the two things. These diagonal elements should be greater than equal to 0, and determinant of this matrix should be greater than equal to 0. So here you can see this determinant. This is actually the matrix. You take the double derivative. Okay. So you can see here we achieved along the diagonal, the elements are either greater than 0 or equal to 0. So all the elements are greater than equal to 0. So first condition is satisfied, and the second condition is that if you take the determinant, it will be equal to 0. So second condition is also satisfied that the determinant is greater than equal to 0. So both the conditions are satisfied, and that's why this is semi-positive, positive semi-definite, and that's why our objective function is convex. Similarly, for the constant, we have to find its Hessian matrix, because the constant Ci, you can see here, Ci is also a function of x naught, y naught, and p naught here, because you can see pi. What is pi? Pi is nothing but the square of the distance, and you can see pi is here given by xi minus x naught whole square plus yi minus y naught whole square. That is pi. So here you can see, if I write it in mathematical form of this constant, this is xi minus x naught whole square plus yi minus y naught whole square minus p naught. So this is your, I am denoting this constant as a function of these three variables. X naught is variable is there, y naught variable is there, and p naught variable is there. Now I have to determine the Hessian matrix. I will not written the Hessian matrix here. So similarly, just like in the previous case, similar to this one, you can find the Hessian matrix for this one, and this is also satisfying both the condition that the diagonal element of the Hessian matrix is greater than equal to 0, and your determinant is greater than equal to 0. So that's why this is also a positive semi-definite, and all the constant, because the constant is going from I to 1 to n. So all the n constants are convex here. So in general form, I have proved that it is convex. So that's why it is satisfied for all I. So all the constants are going to be convex in x naught, y naught, and p naught. So now we will because both constants are and objective function is convex, so that's why our problem is convex. So now if we are going to find the optimal solution for the problem, then it will be a global optimal solution, means only one unique solution will be there, best solution. So here you can see we will try to for finding the optimal solution, we will try to find the KKT condition. So KKT condition, you can also when you will study the convex optimization in a standard book, then the KKT conditions will be described in detail. So KKT condition here we will study briefly. So for that, for finding the KKT condition, we will first find the Lagrangian function of the problem. So here the problem P0 has been defined. So using this problem P0, we will try to find the Lagrangian function. So Lagrangian function is that the objective function will be there, and for the minimization problem, it will be sum with the constant, and the constant will be multiplied with the Lagrange multiplier. You can see here the PTO, this is objective function, sum with all the constants are there. N constant, we have summed all the n constant, and all the constants are going to be multiplied with the Lagrange multiplier lambda. And now we will find the KKT condition. How you will find the KKT condition? We have to take the derivative, first derivative with all the variables x naught, y naught, and p naught, and this constant lambda I pi minus p naught directly equal to 0. So here we can see here, if pi is equal to p naught, then in that case your lambda I will be greater than 0, and if pi is less than p naught, because the constant is there, pi should be less than or equal to p naught. So in your lambda I will be equal to 0, because this is condition should be satisfied. So that's why here it has been mentioned that your constant is going to be greater than equal to 0. Okay. So now you can see here, after simplification of this equation, we can see here these all, you can see the optimal location x naught. I have denoted the x coordinate of the location by x naught star. The star is showing that this is the optimal location. So similarly, lambda star I star is showing that the optimal Lagrange multiplier. Similarly, y naught star is the optimal y location, and p naught star is showing the optimal power allocation over the node S node. So this way we can find the all the x node, y node star and p node star. So this will give the global optimal solution. So this is the set of solution you can see here. So now we can see here. We have recently done some work on green communication. So first we have published one paper in joint optimization framework for operational cost minimization in green coverage constrained wireless networks. So there I will briefly introduce what we have done in this. Okay, 1 minute. I think just give me 1 minute. I am getting some call from someone else. Okay. Okay. So now, okay. So these are the few publications. Okay. We will briefly see these publications. So you can see the first publication that is in IEEE transaction on green communication networking. So there, actually, we try to minimize the total power consumption over the base stations. Okay, in cellular base stations. So we have taken the homogeneous network where the same type of cells are there. So in that, we try to minimize the total power consumption by optimizing the location of the base station and power allocation, means power assigned over the base station, and total number of base stations. So these three parameters we are trying to jointly optimize, and using that we are trying to minimize the total power consumption over the network. And the second work, this is a joint optimal design for outage minimization in DF relay assisted underwater acoustic network. There, actually, we have taken the environment of underwater acoustic network, means inside water. The channel is inside the water. So there, channel behavior is entirely different from wireless communication. So very frequency selective channel is there. Even the your noise nature is also different. So that is also frequency selective. So in that case, we have optimized here. The three nodes are there. Source node is there, relay node is there, and destination node is there, just like sensor nodes. So three nodes we have taken, and here we are trying to minimize the total power consumption by optimizing the location of the relay and power assigned over the source and relay, because here the source and relay are the transmitting nodes. The third one is, you can see that we have taken the optical wireless communication. That is, what is optical wireless communication? This is different from the RF wireless communication. There we are using radio frequency, and here we are using the optical frequency. So So here it is also known as free space optical communication. Here we use optical signal for the transmission. So again here we have taken three nodes: source, relay, and destination node, and we are trying to minimize the total power consumption by optimizing the location as well as the power assigned. So the same type means goal is there, but due to challenges is there due to their different channel behavior, we have approached different solution methodology over different type of systems. So similarly, this work is there. So this is recently we have worked in power line communication. Power line communication means the signal is going to be transmitted through the existing power lines, power grids. So the power poles are there, electricity to which the electricity is transmitted. Poles. So again, we are trying to minimize the power consumption over this system, and this is similar to the fourth one. Here we are using DF relaying, and here we are using AF relaying. So what is DF relaying and AF relaying? I can discuss briefly. DF relaying is decode and forward relaying. Decode and forward relaying. Actually, the source transmit the signal, and the relay receive the signal, and it process the signal, and removing the noise, and then after processing, it again retransmit to the destination. So that is the decode and forward. You can see by the name itself, it is decode and forward. And what is AF relaying? Amplify and forward. Here simply the relay is receiving the signal from the transmitter, and it is amplifying the signal, and it is retransmitting to the destination. So that's why this is amplify and forward. So there are more challenges are there actually in the green communication, because most of the works has been done in similar layer, in same layer, because 7 layers of OSI models are there. So we have optimized the parameters in the same layer. But just like the one of the trade of here we have discussed that the delay is in network layer and power is in physical layer. So similar way we can take the parameters of different layer of the OSI model, and we can minimize the total power consumption. So that we need to be investigated. Okay, so that is the more challenges, more opportunity are there to do the research on those fields. So you can see this is delay power trade-off. So this is the inter parameters trade-off over the OSI models. So these are the brief about the my today's lecture. So okay, I will take some questions from the audience.
Sir, a few questions have been posted on the chat box. They are from the YouTube channel.
Okay.
So the YouTube channel have posted some questions. They are forwarded to you on the chat.
So first question is that what is the outdoor and indoor coverage radius of various cells? So that is already we have seen here. Again, I will open this slide. It is very evident. You can understand easily. So to diagram. So if we go for this slide, you can see here for the coverage indoor and outdoor. Generally, for the coverage around building and house, we use picocell and femtocell. So you can see for the if you are using femtocell, so indoor coverage is you can see around it is covering around tens of meters. Okay, and also in picocell it is covering coverage radius is tens of meters. So both is around tens of meters. So you can see your for the query for your question, the simply answer is that the indoor and outdoor radius of the coverage is tens of meters. What will be the power if you decrease or increase the delay? Okay. Okay, so simply already we have discussed that there is trade-off between power and delay. So if you are decreasing the delay, so decreasing delay is most desired, because no one wanted that in our network lots of delay should be there. So our aim should be there that delay should be as minimum as possible. For that we have to increase the power, because again you can see here this trade-off. If you see this trade-off, power delay trade-off. So here you can see power and delay trade-off. If you are going to decrease the delay, if delay is going to decrease, then your power has to be increased. Has to be increased power, and if you are increasing the delay, then your power should be minimum, going to decrease for a given bandwidth. For a given bandwidth. So you can see, according to our desire, according to our quality of the network, you can tune your power as well as the delay of the network. Okay, so okay, how can we identify the dead node in distributed wireless network? Okay, the dead node actually identification of dead. So many actually there can be bidirectional. Suppose bidirectional communication is there. So suppose the two nodes are there. So identifying the dead node, you can see if you can see if I'm taking this network. Okay, I'm taking it. So suppose these two nodes are there. Two nodes are there, and suppose this is going to be dead. S2 is going to be dead. Then how we will identify that it is dead? So there will be bi-communication. Suppose for detecting whether the nodes are active or working or dead, there should be some feedback. Okay, suppose some test message it is transmitting to this S2, and within a time constant, within a time slot, if it is not giving a feedback to this S node, then S node will declare this is a dead node. So many protocols are there, many schemes are there for detecting the dead node. So this is one of the method that you can find whether the node is dead or it is working. Okay, and okay, yeah, and,
I think there are no more questions. Thank you, sir, so much for taking time out. As we have already mentioned in the introduction of yours, how busy you are with these many things to do in research. So, as well as teaching. So, thank you so much for taking your time, valuable time, and sharing your knowledge with us.
okay.
Thank you.
Thank you a lot for this.
So our next session will resume at 5 p.m. 4 p.m. So see you then.
Okay, Chanji sir. So,
Yes, sir.
should we start the session?
Yeah, sure.
Yeah. Okay. So, good afternoon to all. Once again, we would like to welcome you all in the second session of 4th day of this webinar. I would like to extend my deepest gratitude to our honored speaker, Dr. Chanjit Chaudhary from the Department of EC, NIT Silchar. Before starting the talk, I would like to give a brief introduction about our respected expert. Dr. Chandri Chaudhary is an assistant professor at ECE Department of NIT Silchar. He received his BTech from NIT Silchar in 2006. He served in IBM India Private Limited for 3 years and then joined IIT Kanpur for MTech program in 2009. He did his thesis on stereo vision and its application in robotics. He pursued PhD in IIT Bombay from 2011 in light image compression and application. He was awarded PhD in 2016. His present research interests are multi-view geometry, face recognition, recognition of handwritten characters in multiple languages, novel object recognition. Thank you, Chandri sir, for your session. So you may proceed. Thank you.
Sure, sir. Okay, I'll share my screen. Sir, is my screen viewable?
Yeah. It is with you.
Okay, so good afternoon, everybody. I'm Chandra Chaudhary, and I would like to present on light field imaging. So, though these days light field imaging, with the advent of deep learning, light field imaging has gained a lot of attention these days, and people are actually acquiring lot of results which are far better than what we achieved 5 years back. So what I thought is, maybe instead of going to deep learning, we can first understand what is light field imaging, and then how the image is captured. First of all, what is light field and how capture that kind of image, and then what all we can do with it. So I thought of we can go for one of the concepts like compressed sensing, which is being widely used in this kind of field, computational imaging, light field imaging, all these things. So I thought even in within light field imaging, I'll stress my discussion. I'll narrow down my discussion on compressed sensing. So first of all, let's understand how a camera works. So first, when the camera was built, say here, this box is basically the camera box. So this, the lighter color, the wall of the camera is basically your imaging film. So here actually the image is being projected, and impression is created depending on the light rays, incoming light rays. So now the thing is, how do we allow the light to come in? If the slit here is very big, then multiple rays from a single line, single point of the 3D object will diverge to different points on the screen. So people tried with many things. One of the most successful was pinhole model. So in the pinhole model, what we decided, it was decided was that small slit kind of thing will be a small pinhole will be put in front of the I mean the aperture will be of the camera will be in the size of a pinhole. So the definition of pinhole then becomes how wide it should be, the radius of the hole, how wide it should be. So the narrower it is, the better it is. So it should theoretically it should allow only one ray of light through it. So say if we have this object, say this object is in a single plane, and that plane is facing that this camera, then the light rays are being projected on different parts of the different points of the image film, and an inverted image is created. So the inversion is the image actually is flipped horizontally as well as vertically. So basically this is a 2D camera, we are just seeing the cross section of it. So benefits of this is one ray from one point, one ray goes to a unique point, and that gives a very sharp image. Okay, you have a real and inverted image, you can always invert it back and get the sharp image. But the problem is this impression that is being created on the film takes a lot of time, because every point is being, the impression is at every point the impression is being created by one ray of light. So the amount of energy that one particular ray of light has is very less. So 4 or 5 hours it is to take, where the subject is to sit in front of the camera and the image gets basically captured. So also defining the manufacturing a camera with that kind of slit, that kind of pinhole actually was also difficult. So most of the cases, though theoretically we say that it should be very sharp image with good depth of field and all, but the depth of field is a concept we'll come to, we'll discuss later. So, but the thing is, in reality, the image was, taking the image was tedious and the output was not that good. So what people did is they enlarged this aperture and put a convex lens. So when you put a convex lens, you actually allow all the rays that could pass through the this aperture, you converge them to the lens to a point. So basically this particular film is should be at the focal length of this lens. So given that this object is considerably very far from the camera with respect, compared to this box or the focal length of the camera, focal length of the lens. So this is was the first proposed model, but the problem with this is, if we have two objects here in front of the lens which have two different which are at two different distances from the lens, so one might, the smaller distance the object might be such that it follows the lens maker's formula and gets exactly projected to a point on the image plane. So but if that is the case, any object which is not in this plane or at the same distance from the lens will get projected either in front of the image plane or maybe beyond the image plane. So if it is in front of the image plane, in that case it converges in front of the image plane and then it diverges out. So in the case of this green object, instead of a point, you get actually an enlarged view of the point, so it spreads out. So this is one of the techniques. This concept is used in DSLR cameras these days. That DSLR camera you can adjust the, you have this lens which can be detached from the camera. You can use telescopic lens, you can use the wide angle lens, all these things. So if you adjust that, it's actually a combination of many lens, and if you notice that manually it can be adjusted. So basically you are adjusting the distance between compound different component, different lenses, and they form a compound lens whose focal length, actually effective focal length, can be adjusted. So if I had adjusted at this point, it's such that at this distance the object is sharp on the image plane. Anything other than this distance will form a blur image, and that's why you will find those aesthetically beautiful images where one particular person is in focus and other gradually go out of focus. So then the question comes is, so this is somewhat like this, that you have the object here, it was supposed to focus here, but you put another lens. Here I have put a convex lens. It need not be a convex lens, can be a concave, can be a plano-convex, plano-concave. So, or maybe multiple of them, and you adjust the focal length. And this was supposed to, with one lens, it was supposed to be focused at somewhere near the image plane, but it gets focused on the exactly on the image plane. So this this itself that has an information of depth. This particular object, how far it is from the lens. If you go to the previous slide, so the blue object is on focus. So my lens is, my camera is focused on the depth d, small d. But the objects at anything beyond d, small d, that is here, the green object which is at depth capital D, actually will form a blurred image. So if you move it even further away, then the blur will actually grow. And if you bring it closer, it will actually become smaller, and at small d, it will become sharp 1 point. And if you even bring it closer, then it will again actually form the image, try to form the image beyond the image plane, and that will again create a blurred image. So as you move away from the plane of focus, the image gets more and more blurred. So that itself is a research field called depth from defocus. And there are multiple papers of Professor Subhashish Chaudhary, Professor A.N. Rajgopalan of IIT Madras, who have done extensive work on this. And those were beyond, they were before deep learning era. At present, with deep learning itself, with GN and in general generative based methods, people are able to extract depth from defocus from a single image actually. So what all information does when we capture an image, let's see what all information does a ray of light actually bring to you. So if we have an object, if you say we have the lens, we have the image plane, this is the optical axis of the horizontal black line is the optical axis, O is the optical center, and say this arrow on the right side, extreme right, is your object. Okay. So say at the top of at the top point of the arrow, the rays are originating and they somehow get focused to the image plane. Okay, the lens is such that it focuses at sharp point, let's say. So considering the optical center as the origin for the 3D world, then taking the x-axis, the horizontal axis as the x-axis, the vertical axis is the y-axis, and the axis towards the object is the, or towards the 3D world is, or going out of the camera perpendicular to the lens surface is the z-axis. So first of all, what information we get when we see an image is that what is the color of a pixel? So wavelength, what is the wavelength of the light that has been projected? So that is one information. The other information is taking the optical center as origin. If I find out what is the projection of the object or the point, basically the origin of the light or the point from where the light rays are being reflected. So that point has a coordinate with respect to the with respect to the optical center of the lens. So that is the XYZ coordinate. Okay, and the next thing is, say we consider the middle ray. So that we consider there are basically a beam of rays are coming out of this point and are getting focused by the lens through the to the image plane. So if you consider one particular ray, say the ray that passes through the optical center, so that will have two basically spherical coordinate. There are two angles, so it will have two angles here. One is the longitudinal angle, another is the azimuth angle. So these are also an information that we actually get from a light ray. The other is the time at which the image is being captured. Generally, still image, it doesn't matter which time you've captured the image, but if in case of video, as the frames are being captured one after the other, the time coordinate comes into the picture. So basically, we have now 7 coordinates: x, y, z, lambda, the wavelength, then the angles or the directional coordinates of the light ray, and the time. So 7 coordinates. However, when we capture the image, we get only 2 or 3 information. One is the xy pixel, that is the coordinate on the 2D image plane. Coordinate on the 2D image plane where the light, all the beam of light has converged to, and the color of that pixel or the wavelength of the beam of the light that has converged to that point. So originally we had 7D function. We had a 7D function which is also called lenoptic function. Okay, lenoptic comes from the word lenus, and optic is light. Lenus means all, and optic is light. So lenoptic means basically lenus, all information of the optics, function which depicts all information of the light. So that function, say we consider it as L, all through the presentation we'll represent it as L. So it's a function of 7D, and it is called the light field of from a point, any 3D point, when be it a light source or be it a reflector. We consider it to be a light source. We consider it to be the light field, all the rays coming out of it. So now the question might arise that if we have a mirror and we project a light to it, then the direction is same. The direction of reflection, incidence, and the direction of reflection becomes same. So if we have something like a very coherent light source where all the light rays have the same direction, then when they get reflected, they will also have the same direction. So yeah, theoretically that's correct, but in general, that the mirror actually is called the specular surface. And in general, in light field, in computer vision and image processing, we consider that the surfaces that we come across are mostly Lambertian, and if it's skewed, it is glossy in nature. So Lambertian is a surface from where light rays come out or reflect in all possible directions, are reflected in all possible directions, independent of the angle of incidence. And the glossy surface, on the other hand, is not Lambertian. However, it is not specular also, but it has some skewedness towards the direction of reflection depending on the angle of incidence. So what if we had these 7 dimensions? We actually are now getting only 3 dimensions. If we had all the 7 dimensions, what all we could have done? So first of all, since we have the XYZ, so we can easily create the 3D. So we have just an example I have given here. This is the object that is captured. This is the 2D, and this is the 3D of the object. And this is another. These are from Stanford Light Field dataset. This is called Bunny, and this is called Stone. So Bunny and Stone, quite accurate depth map we get, which generally we don't get that accurate depth map from stereo or maybe multi-view geometry with say 3 cameras or 5 cameras. So here actually we have taken like 16x16 cameras. So okay, we'll come to that. The other thing is that super resolution. Now super resolution actually refers to the field where say an image is given to you, 256 by 256 resolution image is given to you, and what you want to do is you want to increase it to say 1024 to 1024. So 4 times you want to increase it. So first thing Nike says is that you have to low pass it, and then you have to upsample it, right? Multirate, you have to low pass it, and you have to basically upsample it. So multirate signal processing, we have to do that. But the problem is on applying the low pass filter, the image gets blurred. So another problem in super resolution is that noise. The image that we have, that we captured, even if it is blurred, the entire image gets blurred after low pass filtering. But when you upsample it, the noise pixels also come up quite clearly. So given this, when you have the 7 dimensions, say you have the XYZ, you have the angles. Okay, so what you can do here is, since you know the direction from which the light is coming, so you actually can know where exactly the edge of the image ends. If you zoom into an image, I'm not shown here, but actually the number of slides are increasing beyond. So what I can say here is that if you have an image and you you zoom into that image, a particular edge, you will find that if it is a high resolution image, then you will find the edge is quite sharp. You zoom it further, and at a point you will find that the edge is not that sharp. It is basically there is it's a down slope kind of thing. It's not a sharp step function kind of stuff. So that particular thing, if you know the direction of the light, then that particular thing can be estimated. And once that is done, you can register the pixels, that which pixel belongs to which object, and you can exactly recreate the image in a bigger resolution, at a bigger resolution. The other thing is, as I told earlier, the DSLR cameras, you can focus at one point, say in the left top corner. There are 4 images in the left of image. Here, it has been focused at somewhere here at this point. As a result, everything to things, the objects that are closer, objects that are farther away, all of them have turned blur. And when we capture an image with DSLR, we actually capture this image. Maybe this image you have captured, or this image you have captured. Any one of them image you have captured. But if we capture the light field image, in that case we can capture all the we can recreate digitally all these 4. In fact, we can recreate or digitally refocus at different planes, at multiple planes, and that is good because you must have seen sci-fi movies where a green screen. If you see, there are lots of YouTube videos where they show the behind-the-scene shooting of some sci-fi movies and everything. So there you will find a blue or a green screen put, a fluorescent green screen is put in the background, and the actors are acting in front of it. So what they do is graphically replace the green screen with that particular thing, that the background, the necessary background or the desired background, or create that kind of ambience. So that is done graphically. So instead of that, if we capture the image in, say, without putting the green screen, in any condition, we capture basically the video of the actors acting there. In that case, if we can capture the light field, then we can focus on the basically we can create images where we can focus on the actors only. The image is focused on the object, the region of interest, and rest of them are blurred. So depending on the blur, we can say what are the depths or what are the surfaces. Even we can use the depth information here, and we can replace them with the desired content there. So that becomes quite easy and quite cheap. So other uses are enhanced depth of field. Depth of field means if you go to the first slide of pinhole camera, where we talked about that all rays, each ray actually is projected to a unique position on the image plane. So here we are expecting, since it is each unique point is mapped to a unique point on the image plane, so it should be a very sharp image. So it doesn't matter how far the object is from the camera, how close it is from the camera, all of them will appear to be in focus, all in focus it is called. But due to this pinhole matter in this case of pinhole camera, and also pinhole camera, the amount of time it takes and all those things. So you can find actually in cheap cameras, even in your mobile cameras or even in cheap webcams, you will find that you have all in focus images. But if you zoom into the images, you will find that at certain point the image is quite sharp, at other points the image is a bit blurry. So how that is achieved in webcams is that the aperture is not pinhole, but it is not a wide aperture camera. The aperture is quite small, and the lens diameter is small, and the focal length of the lens is adjusted designed such that the ratio between the diameter of the lens and the focal length, so that is called the focal number. So the focal number is adjusted such that a sharp image is formed on the lens, or the CCD, on the CCD behind the lens. So, but the problem still remains that to design such kind of camera so that you have actually all in focus image with very good sharpness, then you actually need very costly CCD, you need a very costly lens, and the manufacturing process also requires quite high precision that actually increases the price of the manufacturing. So enhanced depth of field is as a measure. Depth of field is a measure of sharpness, all in focus image. If all the points in the scene are in focus, and how sharp are they? So depth of field actually means the closest object in the scene that appears to be sharp in the image, and the farthest away point in the scene that is closest to that appears to be sharp in the image, acceptably sharp. So this difference of the distance actually tells me what is the depth of field of the camera. So that can be achieved by light field imaging. The other is high dynamic ranging. So high dynamic ranging means that if you have say in this video call, if I put in any video you must have seen, if there is a window open behind the person, or there is a light source behind the person, the light source becomes so bright, appears so bright, that the person actually, you cannot even recognize the person. It becomes totally dark. So that actually is trying to the system is trying to adjust that if it is viewable, if your face is viewable, then how can the light source, which is quite brighter, can that be accommodated within the range of pixel values? So how to dynamically range that depending on the scene, that is dealt with in the field of high dynamic ranging. So this can also be done with light field imaging. The other work is novel view generation. So consider you have two stereo, say you have two eyes, right? And with one eye closed, let's say with the left eye you look at one point, and with the right eye you look at another point. So at the same point, with the other eye you look at the same point, you will see that the object appears to shift a bit. So if that actually helps us to view 3D. Now the thing is, we have the eyes rolling, they can move. Now in lab situations, we generally have two steady cameras that basically stereo setup, where we have two cameras that are fixed. And if I ask you that if image one, left camera image one is left camera image is given, and right camera image is given, how can you produce what is there in between? Say the two cameras are 10 centimeters away and the images are given, and the question is asked, if the cameras are brought closer, say first camera is kept in the constant position, the second camera is now brought closer to say 5 centimeters. So now what will be the image of the second camera? Can you predict from the previous two cameras, previous two images that were taken with two cameras 10 centimeters apart? So that is one thing people are trying to do in computer graphics. Computer vision and computer graphics generally deal with two different things. Computer vision deals with given images, can I create 3D? Computer graphics, on the other hand, given 3D model, can I project it back and create an image that that maybe is not captured in a camera. So how to capture this light field? So the first attempt was by Lippmann himself. Lippmann was the person who actually got Nobel Prize for color photography, and he actually designed a camera where there were 4 films and 4 lenses, and they were such that they were synchronized that you can capture 4 images of the same object but from different positions, so that gives you some information about light field. So later on in 1996, actually that work actually started from 1992-94. What they did is they created an array of VGA cameras. Okay, so each of them were 1024 by 1024 resolution. So that's about 1 megapixel resolution cameras, and they created 16 by 16 camera arrays, and that frame they actually that kind of 3 such frames they took, and they kept an object and point different objects and placed those arrays at different angles to the object and captured multiple images. So how does that multiple images, how does that give us all the 7 dimensions? So we have say here we have an object and we have multiple cameras. I've put here 4 cameras, maybe there are multiple of them, and in 2D I have given only 1D here. So what happens here is the rays from the light rays from this object actually converge to camera 1, camera 2, camera 3, and camera 4 at different points. So something that I just told, that 2 eyes, if you look at with one eye, the image appears somewhere else, and in the other eye the image appears somewhere else. So there is a disparity. So when you have 4 cameras and you have captured these, so basically you can now know not only one ray, since it has a lens here and a big aperture, not a big, quite an aperture here. So this beam of light that passes to the aperture, you can find out the average angle that passes, that has the angle of the light beam that has come to this camera. And you can find out for camera 2, camera 3, and camera 4. At the same time, you can compute the 3D. So if you can find out this point and this point, so this is the XYZ coordinate. This, if I take the origin somewhere here, then the XYZ, this is the Z coordinate. So I can easily find out with trigonometry easily that what is the this Z coordinate. So XYZ, the directional coordinates, and the color image can be, and the colored information can be captured by this. But the problem with this is that it requires a huge framework. It's a huge framework. You cannot carry it outside the lab, and to process it, there comes a computer. So you need quite a good computer for processing so many cameras together. So then in the same lab of Stanford Light Field Imaging, they came up with this Lanoptic camera. What they did is, there is a lens, there is the image plane. So instead of, so this is not a single lens, this is a compound lens. So instead of just keep allowing the light to project on the image plane, they have put an array of lenses here. These are called micro lenses, okay, or lenslets. So lenslets, array of lenslets are put here, and the distance between the lenslets and the image plane is the focal length, and the distance between the lenslets and the compound lens is again the focal length of the compound lens. So any light beam coming in converges to the optical center of a particular lenslet, and it is basically diverges out on the image plane. So 1 pixel, in earlier what we saw is the image plane, 1 pixel, basically the beam of light is converged to 1 pixel. So here, that one point where it was supposed to converge is now being diverged out to an area on the CCT. So here on the right side, you will find how a raw image, a captured image from this kind of camera looks like. So if you take a particular block, we have enlarged this part. So here, in the enlarged small block, you will find each circle here is basically one pixel, how it would have looked if there was no lenslet. So instead of converging all these light rays to one point, they have diverged the points, the rays to different points. So that actually gives me that different pixel here will contain rays or beams, small beams of light from different angles. But they represent, the entire circle represent a particular point in the 3D scene. So we have here basically one point, the light originating from one point that can pass through the main lens of the camera, the aperture of the camera, being diverged out to a group of pixels, and each of the pixel gives me the directional information of the rays that are being focused on that particular pixel. So here we get the angular information, and we have basically the what you call the XY or the pixel coordinates here. So what we can do here is, say I'll take the center pixel of each circle. We have the circle, we have an array of circles here, right? So we'll take a center pixel of each circle, and we'll form an image. So that image is basically the image of the scene seen from a particular angle. Similarly, if I take a different position and the same position in all pixels, different position, say P1 within the circle, pixel at P1, and I take P1 pixel from each of the circles, okay, the pixel at P1 position in each of the circles, and I make an image. And then that image, basically I stack them together and form an image, digital image. So when I form that image actually gives me the scene being viewed from a different angle compared to the previous one. So in this way, I can generate different images, multiple images. I have angle information, I have multiple images. So basically I can compute X, Y, Z. I have theta and phi, and I have the color information. So that gives me the light field. But the problem with this camera was, actually this camera, this concept was the base for Light-Tro. Light-Tro came up in 2006, 2007. Light-Tro came up. There's a company by the author of this paper, Ren Ng of Stanford University. The problem was that here, one pixel is being converged to a circle, or I should say it is getting diverged to different, basically a group of pixels. And the group of pixels is though capturing the angular information, but this actually is reducing the output final images resolution. As I told that, I just said now that if I have to form the image, I'll take one pixel from each circle, stack them together and form the image. So how many pixels can be there? So there can be pixels as many circles are there. And then how many circles are there? That depends on how many lenslets are there. So you might have a 4 megapixel CCD or say 16 megapixel CCD. But since you have like 1 megapixel, or 1 million of these lenslets, you can at best get 1 megapixel image, not more than that. So that actually was a severe backdrop of this method. However, in Adobe systems, Todor Georgiev, he actually improved this method. What he said is, I did not keep the images, the lenslet and the lens at this distance, that here it should be focal length, here it should be at a focal length of the lenslet should be at the focal length of the main lens, and the image plane should be at the focal length of the lenslet or the micro lenses. So what he did is, he said that if the face that the middle image that you have, so here, if you have a 3D object, say human face, and it is getting converged through a compound lens of the camera, and an inverted image is formed within the basically inside the camera body, not on the image plane. So basically what he's saying is that when we had here this kind of thing, this scenario, so the green object is being projected to this point. So the sharp image is at this point. Maybe other object might find out its position here, here, here. So I can find out a 3D object, a 3D image formed here. So what he did is he modeled the lenslet array as array of cameras themselves. So now the image formed by the main lens of the camera, the 3D image formed, the 3D projection formed by the 3D, the face, the real face object by the compound camera, compound lens, becomes this particular thing, now becomes an object for this lenslet array. So they now behave as an array of cameras that are viewing this thing. So basically he has what he has introduced here is that if this is the object, say A is the image, sorry, not the object, the image formed, and this lenslet array is put, and they are observing the image. So they will basically have their own field of view, and depending on the field of view, they will view only part of the object. So different parts of the objects are formed in the image plane. So how to create the final image is basically you correlate between them and the array of images that has been formed, and you take parts which are novel. Say in the A, this is the pinnacle part, this is the middle part, and this is the base part. So you take cut off these three parts from these three images or sub images, and you form the final image. In this way, the resolution, though the resolution of the image compared, say in 16 megapixel, we said that since there are 1 million lenslet, only 1 megapixel image can be formed. Here, on the other hand, I'm not taking 1 pixel from the image of a lenslet. I'm taking a part of the image. As a result, it can be like 5 or 6 megapixel, or maybe goes till 8 megapixels. So that is an improvement, but still CCD, all the resolution of the CCD is not being used. But still, it has been accepted and by the industry, this concept, and Raytrix camera was formed. Now the first image, coming to the first image, this is how a lenslet array under a microscope looks like. Okay, so it's a hexagonal pattern they have taken. So what earlier image we saw is that circular, and it was not hexagonal pattern. So in between the image, there are lots of dark parts which are getting wasted. So in this case here, we have a hexagonal pattern. So that has the tightest backing, hexagonal grid, and that actually is able to use most of the pixels of the CCD, most of the transistors of the CCD. So this was one concept, and the problem with this lenslet based or capturing light field is that here we are dealing with the optics or optical physics of this camera, and manufacturing lenslet. I've put a link here, demicon.com. They are one of the dealers who actually you can order, you can basically custom design your lenslet array, and you can order for manufacturing. They can manufacture an array of lenslet and send it to you. The thing is that there are a couple of them in this manner, but it is very costly affair. And recently there has been many attempts. Instead of a flat array of lenslets, people are using a curved array. So a concave or convex kind of lenslet array are also being tested. So this is one of the methods. So Lanoptic camera, that was what RANNG did was Lanoptic 1, it was called, and what Todor Georgiev and Andrew Lundstein actually proposed was Lanoptic 2. So this is how the image looks like. In general, there is very small difference in the image. You just with blank eyes, with naked eyes, you will look. It will look like a blurred image or image gone out of focus. But if you focus in, you will find that there are small images formed of the different angles or different parts of the image viewed from different angles. Okay, so that gives the multi-vision effect. So then there is another method, another group of methods that people have been extensively trying to they have exploring, and still they are exploring this kind of thing. is that what if we don't use a lenslet? Instead, we'll print a mask. What I mean by print a mask is that you can take something like a translucent page, something like the plastic page, and you print a random mask over that, a matrix over that, something like this. The right hand side, you will find a matrix with random values, something like this. So how the image is formed here is, you have the lens, you have the object, and these rays, when converged to the image plane, they pass through this coded mask. Now this coded mask, if you vary the values, say from 0 to 1, okay, so if somewhere the value is 1, the ray passes without any attenuation. But if the value is 0.1, 0.2, 0.5 or 0.9 even, there is a attenuation. As a result, the image formed at the image plane, the point, the pixel formed at the image plane, sensed at the image plane, that actually the value now changes depending on which part of the mask the rays have passed through. Okay, so we'll look into this in details, because this is the more recent things people are trying to do. So one is coded mask based method. So first thing is that when we had without the coded mask, if you have the image plane and the lens, and the beam of light being converged to one point, say this light field, I have taken here x and a, L as x, as a function of x, small x and a. Small x actually tells me x and y, that is the point on the surface of the lens. Point on the surface of the lens on xy coordinate. It's a 2D surface we are considering. So it's a x and y coordinate is sufficient to denote a point on the surface of the lens. And a is the angle, or the 3D angle. So it's a 2-dimension, so a longitudinal angle and azimuth angle of the light rays. So when the image is being formed, so it's the light field. This is the light field within the camera after it has passed through the main lens of the camera. So all these light rays being integrated at a particular point x for all the angles. Basically, I'm integrating over all the angles. All the angle or rays of all angles that converge to x are added up, and the pixel or the image at pixel x is formed. Okay, so say we have the angles. Say we discretize it. We need not consider all the possible angles. So let us take angle 1, angle 2, angle 3, and angle n, say n beams we created that. These are the discrete angles possible, and this angle value can be at best, and maximum value that this angle can take is the solid angle formed by the projected by the lens that on the image plane. So solid angle is basically the angle of the cone. So here it is a triangle form, but in 3D, the lens will project the light rays in the form of a cone to convert the light rays in form of a cone to the image plane. So the angle of the cone is basically the solid angle. So let's say this is the image formed Ix. So this integration, what we have done here, what they have done here is they have taken phi j, a weight they have put, and it's a weighted summation of the light field at angle j. Ix is equal to Lx Aj phi j. Okay, so as phi j changes, how phi j will change is basically depending on which part of the coded mask the light ray has passed. So that is the weight. If it is 1, then if the value of the mask at that point is 1, so there is no weight to be put, so there is no attribution. Otherwise, it is less than 1 and go till 0. So generally not 0, 0.1 or small values are taken. 0 is of no use to us. So these light rays, weighted combination of these light rays gradually forms this Ix. So how phi j and Lx Aj we can form is, phi j we can write it as a diagonal matrix. And LXJ is basically an array or a vector of all the rays at angle J in position 1, 2, 3, 4, and so on, at different positions of the on the CCD. So at different positions for a particular angle. So if this is the angle of here, maybe, or this is the angle here, maybe some other ray has come over here with the same angle. Okay, so that is a value, that ray will come up here. So LX1 AJ is basically at X1, what is the light ray with angle AJ. At X2, what is the value at AJ is LX2 AJ, and so on to K positions. Say there are K positions to be considered, K pixels to be considered. So if we consider that the entire light field, that is, we not only consider initially what we said is at a particular angle. So if we consider now the light field, that is all the positions, all the angles, then we need different phi j's now, phi 1, phi 2, and so on to phi n. Okay, so n is basically the dimension of the number of angles we're considering here. So the phi now becomes something like this, and multiplied this this equation earlier that we have, summation equation, now becomes something like this. Okay? So we have basically concatenated all the phi j's together and found the phi and multiplied the phi to LXA, and that's how we can get IX. So now IX is also when you multiply this with the LXA. So when these two matrices are being multiplied, or this matrix is multiplied with these two vectors, with this vector. So this row gets multiplied with this. Okay. So here we have R11, then we'll have 0, then we'll have R21, and then we'll have 0, and so on in this manner. So the first element, if each phi j is non-zero here. So when you multiply this with this first row, actually you get R11 LX1 A1, R21 LX1 A2, and so on. So basically you will get all the light rays that have converged to X1 with angle with different angle A1, A2, and all possible angles you have considered. So now R11 is the R11, R12, these are the values that we have put on the coded mask. So when we take the weighted sum, when you multiply these two matrices, basically each row of the output is basically a weighted sum of the light field at different positions. So basically that is the image vector. So once this is done, so depending on these values, basically if this is the pixel, and we can find the cone, the solid angle. If this is a pixel, if we have the solid angle, then we can back project and find out which all parts these rays have passed through, and actually we can find out these, you can say, the values of the mask that has created this kind of image here. So if we have multiple images, then also the same thing. Multiple objects, then also the same thing. There might be overlap, two rays, objects from rays from different objects passing through the same coded aperture, but that's not really affect the image, because there might be a little bit of diffraction while passing through the this coded mask, but that does not affect the output that much. So how does what does this LX, this vector here, the light field vector, looks like? So basically we have LX1 A1, LX2 A1, and so on to say so on to LXK A1. That is basically all the pixels at all the pixels light field, the light values or the pixel values at all the positions that are being viewed from angle 1. So we'll have an image, and then angle 2 another image, angle 3 another image, and so on. So we'll have an array of images. So this multi-view images are basically this light field vector. So now the thing is, generally, if we can represent in image compression as well as in methods where inverse problems kind of thing, we always look for sparsity. In compression, the sparsity is in the sense that the energy is compressed, and in inverse problems, the sparsity in the sense that since it becomes an ill-posed problem, there are multiple solutions. We try to find out the unique solution by saying that the solution has to be sparse. So this, if we take this light field and project it to a transform, okay, say if we take the density, okay, so when you take density of a vector or maybe an image, 2D density of an image, you actually are projecting the image on basically basis vectors, density basis vectors. So say in case of 1D vector, you will have a matrix representing the density transform, where all the vectors of the matrix or the columns of the matrix are the basis vectors of the density domain. So here, let us say we have a transform D, and when projected this vector on D, LXA, when projected on D, it gives me theta. So LXA is equal to D into theta. So what we have now here is, we had earlier Ix equal to phi LXA, and we had Ix, and now since LXA is d theta, we have Ix equal to phi d theta. Now if you go to the previous slide here, okay, so here you have this image K, this on the left hand side of the equation, you have K elements in the vector. In the right hand side, the matrix that you have, that is K by K into N. So it's a huge matrix you have, and then the light field vector, which is again your K into N. So what we have here is, we have a system of equations. It's basically Ax equal to Y, or I should say Y equal to Ax in this sense, in this case. So the left hand side, Ix1, Ix2, Ix3 to Ixk, these are what I have sensed with the image. When I captured the image, this is what I've got. With the coded mask in front of the image plane, this is the image I have got. The matrix represents the coded mask. So since I have designed the coded mask, I know the matrix. But the light field vector in the extreme right, that Lx1, A1, Lx2, A1, and so on, this vector is unknown. And the problem here is the number of unknowns is much more higher than the number of equations. So this is called an underdetermined system of equations, and it is ill-posed. Now, the classical definition of ill-posed problems is a problem that is not well-posed. So question arises, what is well-posed? So well-posed is basically a problem whose solution, first of all, there is a unique solution. And when there is a unique solution, the solution will change as the input is, or the observations are changed. So you have Ax equal to Y. So when Y changes, X should also change. So if X is not unique, okay, say A is a matrix which is not a full rank matrix. So in this case, what we have is short and fat matrix. So basically, number of rows is less and number of columns is more. So it's not a full rank matrix; it's a rectangular matrix. So inverting this matrix is not possible. So if you go for pseudo inverse, also there is a high chance that you will get a skewed result, and maybe you will get a rubbish output. So not maybe, actually you will get a rubbish output here, because the matrix is very, you can say, ill-conditioned. The eigenvalue of the matrix, the minimum eigenvalue and the maximum eigenvalues, the ratio is very skewed in nature, at the extremes. So what you have to do here is, generally, in such cases, in inverse problems, we choose constraint. Since we have y equal to ax, that is in this case ix equal to phi d into theta. So phi d is my a and theta is the x. So to find x, that is theta, I'll say that theta is very sparse in form, sparse in nature. Sparse means if I have a vector, n-dimensional vector, x equal to x1, x2, x3, and so all stacked in a column to xn, say maybe most of them are zeros and very few of them are non-zero. People who have worked with DCT, they must have seen after an image being transformed with 2D DCT, very few values actually, the low energy end of the frequency of the spectrum, you will find values which are quite dominant, and higher frequencies are quite negligible. So that's how JPEG compression works. So you consider, you don't consider the negligible values, you consider only the dominant values, that is the low frequency values. And it has worked very well for us till now. So in this case, d theta that we have taken, d, if we design such that the transform matrix, if we design d in such a manner that when the light field is projected on d, then theta, that is the coefficients, d into theta becomes my light field, then theta is sparse in nature. Okay, so let us first understand this particular thing, that minimize first norm of theta such that Ix equal to phi d theta. So first norm, generally norm is, we all know, is of this form, as theta p, pth norm of theta is basically, if theta is a vector of theta 1, theta 2 to on to theta n, then basically we have mod of theta 1 to the power p, mod of theta 2 to the power p, and so on to mod of theta n to the power p whole to the power 1 by p. So if you consider p to be 0, if you consider p to be 0, then within the bracket you have this mod of theta 1 to the power p, mod of theta 2 to the power p, and so on. If theta 1, theta 2, basically theta j, if theta j is not 0, you will get a 1. If p is 0, then non-zero to the power p or to the power 0 will give you 1. If p is, if theta j, say theta 3 or theta 10 or theta 4 is 0, then it turns to be 0 to the power 0, which we do not consider because it's absurd, so we don't consider that. So we consider only those values that are non-zero, and that entire thing will become a summation of ones, and where all we will have ones, where you have non-zero values. So that's why the 0th norm is a counting norm, and it tells me how sparse the norm or the vector is, where all there are, how many positions are there where there is a non-zero value. Okay, so but here we have taken theta 1. The problem with theta, we have taken the first norm of theta, L1 norm of theta in the optimization problem. The problem with 0 norm is that optimization, we cannot take the derivative of that. So if we consider the norms, basically L1, so the circle external, the exterior circle is the L2 norm of, say, theta is a 2-dimensional vector, theta 1 and theta 2 are the 2 coordinates. Then if you consider the L2 norm, say p is 2 in this case, then you get the Euclidean distance, basically Euclidean length of the vector theta 1, theta 2. So that turns out to be a circle. If you take the first norm, you get a diamond kind of thing. So basically a bit rotated square. And if you go below 1, it turns out that these edges of the square that you had earlier, the diamond that you had earlier, curves down and it forms a spike. This particular diagram is for p equal to 0.5. If p goes beyond that, gradually to 0, you will get this. It will touch the axis. So basically, in that case, you will have only, say, if I consider this axis instead of this diagram, if it was this axis itself, that means I'm considering for any point on this axis on this diagram, either theta 1 is 0 or theta 2 is 0. So that makes it sparse. But we are considering this diamond here. So that is first norm, and it turns out it works well for, it is sufficient for sparsity minimization, or sparsity constraint minimization. So let's see how. So we have the second norm of theta. We have y equal to x, say Ix equal to phi d theta. So this is y equal to x. So this is like a plane, and theta 1, theta 2 is the circle, L2 norm. L2 norm of theta 1, theta 2, or theta itself is this circle. So this point where they meet is the point where this condition is satisfied because it lies on the line, and it might be that this is the minimum or it is the minimum value of theta at which this occurs. Okay, but the problem is it is not sparse yet. It is not sparse yet here. So what we started with earlier is that we want a constraint that such that when we put the constraint, even if our y equal to ax, the set of equations was underdetermined, more number of equations, less number of equations and more number of unknowns. So there are multiple solutions. So what you do is you put this constraint of sparsity, and there is a high possibility that only one of them is that sparse, is the sparsest of them, and you select or pick up that one as the solution. So that gives you the unique solution. So if you consider the L1 norm now, this actually here, the point where it meets has a high chance this will meet at the point of the on this axis or maybe this axis. Okay, so that's how regularization had worked till now. But the problem, so that way it had worked for regularization problems, but this is a constraint optimization. So here it might turn out the situation is something like this, that the line intersects the diamond at 2 points. Okay, so though it may be the minimum L1 norm of theta 1, theta 2, but still the problem exists that you can have multiple solutions. So one of the properties of a matrix that are taken is called restricted isometry property. Okay? Isometry generally refers to isotropy, isometry. Iso actually refers to uniformity. Okay, and metry is generally for metric definition of distance. So isometry means that ax norm, norm square or the second norm square must be within a limit of x norm x square. So if norm x square was this circle, 1 minus delta k is a positive value, then 1 minus delta k will basically be a circle inside this circle, and 1 plus delta k will be a circle beyond this circle. So within this limit, ax square should lie. Okay, so this is why it is called isometric property, because even after transformation of A, even after transformation by A of x still has this property that norm of x lies within this and this. Okay, so this holds for the property should hold for a sparse vector. X should be a sparse vector, that all most of the elements or coordinates of the vector x should be 0. Most of the values should be 0, and very few of them should be non-zero in nature. Okay, so the meaning of restricted isometry property, actually Donoho and Candace Tao, they had given an extensive explanation of restricted isometry property, and Donoho was the person who actually derived that restricted isometry property is sufficient for this case. What this says is that A is the matrix. Now say we had the d theta, the matrix that we had earlier, what was a short and fat matrix. So the number of rows were less, number of columns were more. So there is a high chance, or most of the columns will be linearly dependent. There are a few columns which will be linearly independent. So what it means, the restricted isometry property, is that if I take any k number, say k is the sparsity value I'm looking for, that is k values in k coordinates in x should be non-zero. So if I take k number of columns, any columns randomly, and I form a submatrix with those columns of A, the k columns of A, and I take the transpose of this and multiply with this, basically A's transpose A's, then it should be close to the identity matrix of dimension k by del k. Okay, so del k basically it should be within orthonormality, say in a sense saying that within orthonormality within a distance of del k. So this is a near orthonormality condition actually. So problem is that it is very difficult to construct a matrix which is actually restricted isometry in nature. So the next thing is that can we actually do this without the RIP condition? So let's look into the optimization problem now first, that minimize theta, first norm of theta with the condition that Ix should be equal to 5d theta. So we have this Lagrange, this we are trying to formulate it with KKT conditions. So with Lagrange becomes del theta 1, del theta norm 1 plus lambda transpose into Ix minus 5d theta. So this particular thing, I have taken here del transpose because it might turn out that there are multiple of this del, and this particular Ix minus 5d theta is a vector itself. So the KKT conditions now actually the differentiating with respect to, so here in this Lagrange, the theta and lambda we have, theta is the primal variable and lambda is the dual variable. So when you have differentiate with theta, you get this, and when you differentiate with lambda, you get this. I have straight away equated it to 0 in this case, but it's not correct actually. It works for this case, but it should have been epsilon here. That 0 belongs to this kind of thing. This may not be 0, but it might give up many values. 0 might be one of them. Okay. So taking this into consideration now, so this is the first equation that we have is nothing but the constraint, and the second one that we have, it's quite interesting. We have del of first norm is equal to phi d theta transpose lambda. Okay, so if we consider phi d transpose phi d as A, so A transpose lambda is a vector. So that is basically range of A transpose. So when we have this, then you can say that for there exists a U in the range of phi d theta such that the vectors of U are basically sine of lambda I, Ui, if lambda I is not equal to 0, and Ui if Ui belongs to -1 to 1 otherwise. So I'll give you some time to think about it. How this comes out and how are we taking the derivative of first norm here. What we have here is when we are differentiating first norm of theta, we have to differentiate the mod values of theta 1, theta 2, theta 3 and all these things. So each of these mod of theta 1, say from 0 plus and from 0 minus and to infinity and to minus infinity. So not considering the 0 point, the discontinuity point, because we know that mod of x or mod of any theta 1 or anything is basically a V-shaped curve that has its origin at the 0, 0 or the origin itself. So origin of the coordinates. So that is the point of discontinuity. So instead of that, if we consider only the part where it is not discontinuous, in those regions, you will have Ui is equal to sine of lambda I. And Ui may be from -1 to 1, somewhere from -1 to 1, if it is equal to 0. So at the point where it is 0, it depends how your what your differentiation output will be, and the problem will be that it may lie anywhere from -1 to 1, cannot have a distinct value. So the thing is here that how I get Ui is equal to sine of lambda I. So you have this phi d theta transpose lambda is equal to d of difference del of theta, first norm of theta. So if you consider del of theta 1, then you will have phi d transpose into lambda 1. So the sign of lambda is the one that you will have the first row of phi d theta, phi d transpose being projected to the basically your lambda vector, And when you differentiate the theta I, you will get that it is actually the theta I, lambda I, that is getting. So basically what I'm saying here is that you have y equal to ax, or if you have here phi d as a, phi d transpose as a and lambda as x, then ax is basically a straight line if I consider. Then differentiating theta, basically I get the sign of lambda I in case of first norm. So either it is on the first quadrant in case of two-dimensional. So either it is in first quadrant or it is in second quadrant, and depending on that, you have a +1 or -1. So in this case now, if ui belongs to -1 to 1. So if u1 is 1 and u2 is sine of theta 2. So basically I have in since I'm optimizing theta first norm of theta, there is a high chance that basically, okay, here I made a mistake. It should be sine of del 2, lambda 2, not theta 2. It should be sine of lambda 2. So there's a high chance that u1 is 1. That means theta 1 is 0, and this particular thing is non-zero. So in this case, if u is here, in the u1 is 1 and the sine of u2 theta sine of lambda 2 is here, say +1. In that case, I'll have the point here, so the u will lie somewhere here. In the u is here, so the line passing from 0 or the origin to u is basically the range of phi d transpose, and that's why the range of phi d will be orthonormal to it, and it will lie on the basically norm of theta 1, theta 2, and that will give you multiple solutions, and that was what was happening in the earlier case. So instead of that, if we just reduce this constraint that ui should lie between -1 to 1, if we make it an open bracket, so in that case we are excluding -1 and 1, then u1 and u2 cannot become -1 or 1. So if it is less than 1, in that case, this range of phi d transpose actually goes a bit away from 45 degree, and that in turn rotates the range of phi d, and that's why ix equal to phi d theta. So range of phi d is the space where ix equal to phi d theta will lie, and that will intersect the first norm at a single point, and that will give us a unique solution. So that is one thing, and how to implement it. So there are lots of implementation techniques for this. So one is KSVD, most popularly used. So the other one, basically the first technique you need to learn from for KSVD is orthogonal matching pursuit. So that is a basis pursuit class of optimization techniques, approximation, not complete exact optimization. It is a approximation technique. So KSVD generally is used for train this dictionary to calculate phi and basically d. We already know phi, so what we want to design is d. So the entire procedure now is that we had put a coded mask in front of the image plane. We had the lens, and the ray were converts to the coded mask, and we had this pixel, basically weighted average of the intensity of the rays passing through the coded mask. So when we had this, the problem was we had this formulation that we want to minimize theta 1. We want to find a theta with minimum first norm, and such that ix equal to phi d theta. So once we find out that, if we now multiply d into theta, we'll get the light field, because phi into the light field was the coded aperture operation. So phi is the coded aperture matrix representation of the coded aperture. When that is being applied to the light field, we get the image that is ix in the left hand side here. So d into theta is light field. So since we can find out the d from KSVD, minimizing this optimization problem, we will get the theta, and from there we can find out the light field. So this concept of compressed sensing was also used in our work This previous work was MIT Media Lab, Camera Culture Lab work, and by under Dr. Ramesh Raskar. And then this particular concept, one of the problems with multi-array imaging is that we have I just showed you that Stanford array of cameras. So 16 by 16 cameras will capture 16 by 16 images, color images, and that too, each of the images 1024 by 1024 megapixel resolution. So when you have 1024 by 1024 pixel resolution, so that's 1 megapixel resolution. So when you have an image of that resolution and 16 cross 16 such images, storage becomes a problem. So it's going to capture a lot of memory on your hard drive or SD cards. So compressing the light field images. So compressed sensing was used here. The thing is, we have this array of 3 by 2 images, and from first image we take random pixels. The second image we take another set of random pixels, and so on. And the condition is that the random sampling we are doing from each of the images should not repeat itself. That is, the pixel positions that we have taken from the first image none of the pixel positions should repeat in the second image, or in the third image, or in the fourth image, or so on. So the image that is formed by taking random pixels, same number of random pixels from different images but at different position, is of this form. I've shown here a grayscale image. This image, if you take a small block of it, zoom it, you will find it is of this form. The reason of this at the edge being shown up, this kind of thing, this scattered kind of thing, is that in these images, the difference is the camera position is changing. So when the camera position is changing, the object will move with respect to the object will appear to move with respect to the image, with respect to the camera, and that will be depicted in the image. So these edges of the object will appear to move the most. And that's why when you take random pixels from different images at certain positions, say this here, maybe are from the same image where the object appeared here. These, on the other hand, the black regions are maybe from an image where the object had not appeared in this region. It was from a different position of the camera the image was taken. So depicting this in this form, representing this in this optimization form, that the coded image, this image is I, the process of random sampling these multiple images is phi, D is a dictionary that we have learned using KSVT, and theta is the coefficient to be found, such that theta should be, the L1 norm of theta should be minimum. So the optimization was done with OMP, orthogonal matching pursuit, and it was found that this particular technique actually works for these image in the low bit range. In the low bit range, this is the JPEG. The green one is the JPEG 2000. How much compression it has done, and how much PSNR value basically it is showing. And the blue one is our method, and we can see that the PSNR for very low value, even the PSNR is above 26. So for light field and even for surveillance kind of work, this 26 dB sometimes can be used for 3D reconstruction, or even for light field. Actually, if we can reconstruct of the light field atoms, it is called, from these images can be done, and using that quite a good 3D could be formed. And that 3D actually one of the samples we showed in the previous slides. So this is the actual image. So it was compressed with light field and then reconstructed back, and even at low bit range, this was the 3D that we got. Obviously, there are some errors in edges, but as overall, this image accuracy was found better than normal stereo matching techniques. So this was the compression technique, and so where does the future take us to in this case? So at present, there are lots of learning-based methods that people are trying to do. For example, if we have a generator that can be trained, that given a light field set of light field images, it will actually generate a dictionary. Okay, so when it forms a dictionary, how do I know the dictionary works? So I apply it to the previous, where I had captured the light field and I have captured the compressed sensed image, and I apply the entire thing, the coded mask, everything, and I apply this dictionary that has been generated by the generator into this, and I find out theta, and then the light field is reconstructed. So these light field images and this light field here are compared, and how well they relate to can be stated by the discriminator. And depending on that, if it is able to, it is not able to say how good is the if it is able to say that this is generated dictionary, basically this light field is not the original light field, then that means the dictionary needs to be changed. The dictionary needs to be more accurate, so that we train the generator. Otherwise, we train the discriminator, because we know that the light field is generated, and the discriminator is not able to decipher or distinguish it from the actual light field. So these are this is a technique that is widely being explored, and this will actually help us for cheaper means of light field techniques, because even though the coded mask appears to be very cheap, that we can print on the cellophane paper, we can print the mask, that this random matrix on a cellophane paper. But the thing is, to print this and make it work, you need a high resolution printer. Generally, we don't have that kind of printers in work of places or in offices. So that resolution is called dots per inches, DPI. The high DPI printer is required. So in that case, if with learning methods we can, with a normal printer, if you can print a coded mask, and instead of applying, we can try with applying. People are actually trying it, applying it in front of the lens, in front of the CCD, and sometimes even inside the compound lens, that is between two consecutive lenses. So learning methods also gives us better rendering. So there is a paper by Google where they have Google Mind. They have actually given a video, light field video. So you can actually click on the video frame and change your perspective. It will be like watching a real scene in a running time. So you can actually change the perspective, and the perspective change is not just shift of the frame, but you get the entire 3D perspective change. Okay, so that is all, and these are the references I found during my PhD and till now. Compressed sensing to be really worthy reading for. These are the references that actually, these are the works that actually led to compressed sensing that is there today. So not all of this I have used in my presentation, but I prefer to show them because somehow or the other they have contributed to the entire thing. Okay, so is there any questions from the audience? Chat box, okay. So one question is, this is a good question here, that is there any chance of getting the Lenoptic function for the simple RGB image formation? Yes, people are trying to do that. For example, I'll give an example like, say you have a prism and you shoot a light ray through the prism, and the waves you are formed on the other end, actually the pattern will change as the direction of light changes. So instead of a lens, just a lens, if you can mix and match some other optical device, you can actually do this. And RGB image formation also actually, just simple RGB formation, if you can explore, get a hand over the bare pattern of the image, there are actually a couple of people, no published work I've seen till now, but personal conversation with them, actually they said that there are chances that bare pattern of the image, basically CCD when it's manufactured, it is one of the costliest part in the camera, the lens and the CCD. The better these two are, the better the camera quality is, and the better the precision method is. So this CCD, it is not possible to basically each of the transistor is a band filter, okay, band pass filter. So in that band, RGB, all these values, it is not possible to to gain. So what you do here is you take in a repeating pattern. One transistor will sense red, other transistor will sense blue, other transistor will sense green, and so on. And in a circular way, you repeat it in different patterns are there for generating Bayer pattern CCD. And depending on that, actually, people are that Bayer pattern image, people are considering of using different. Can we actually consider convert it to a light field image? The reason is, even though there are methods that single image I can create 3D, but light field is not just 3D. If you know 3D, then also just by changing the perspective, in stereo vision, when you find 3D, there is a concept called occlusion. That what I see in the left eye and what I see by the right eye, there are some portions in the two images formed that I don't see in both the images, in both eyes. Okay, so that occluded part will come up in the 3D. So from single image, you can find a 3D that you view from that single image angle, but when you want to change the perspective, global view generation and all, you don't know what's beyond or what is the region that is getting occluded by the nearer object. So that actually people are trying that Bayer pattern. If 1 pixel there is a value in a green sensing transistor, if nearby green sensing or blue or red sensing transistor, what values they have, from there can we find out the direction of light. Okay, so that needs a lot of work. You need to know actually the exact parameters of the camera, the lens, what are the distortion parameters of the lens, what are the basically the intrinsic, extrinsic parameters of the camera, especially the distortion parameters of the lens, and that is very tough to find out this so accurately. Okay, is there any other question? Okay, from where can we get the data set of these light field images? So Rahul has asked a question, where do we get the data set of light field images? Okay, there are lots of websites. There is Stanford, there is your MIT Media website, where they have actually both light fields they have captured with multi-array cameras, with Lightro cameras, as well as with basically synthetically developed light field images. So even in UCLA, Berkeley, there are in TM, this Technical University of Munich, there are websites and there are data sets, so you can download them from there. Okay. Okay then.
Okay, thank you. Nice talk. Okay, so now we are concluding this session. Okay. So we would like to thank Dr. Charanjit Chaudhary for taking out time from his busy schedule and providing us with an opportunity to learn from his wide range of research experience and knowledge. We assure it has been a big learning experience for all of us, and all the participants must have benefited and noted down ideas from their future research work. We hope to get such opportunities in near future also. Thank you, sir.
Thank you, sir.
And thank you all attending. Thank you all for attending today's session. The next session will be tomorrow at the 22 sir. Thank you.